This is our CICS seminar. We're happy to have one of our own, Matthew Zahr, joined the department just a few months ago via Lawrence Berkeley National Laboratory, I will assume, and before that he did his PhD at Stanford and his bachelor's degree in civil and environmental engineering, so you're an engineer at the University of California at Berkeley.
Yep. All right, thank you very much. So I'm going to talk to you guys today about my research that is, if I were to describe it in as few words as possible, it is integrating optimization and computational physics. And there's a number of reasons you want to do this. I approach this really from two different directions that are not particularly related, but they do involve all of the kind of these same ingredients. That optimization and computational physics both come in here quite strongly. So the shortest and briefest outline of a talk ever, I'm going to talk about two main ways that I do actually incorporate optimization into this framework. First one is going to be what you would kind of think of when you think about optimization-based physics, is that I actually want to use numerical optimization to somehow design or control a system to improve its performance in some way. That's what would be more the most canonical example of using optimization in a setting. But you can also use optimization in, let's say, more creative ways, where all you care about doing is analysis. I want to do some analysis on some problems that are very hard and very difficult for one reason or another, and I'm going to talk about one application here, which is problems with shocks, discontinuity, something that's very hard to resolve numerically, and you can actually use optimization to get better numerical outcomes, as I'll show. So let me just start with, I'm going to get myself confused here. The first one, optimizing physics. So optimization problems show up everywhere in science, engineering, medicine, whatever you want. The most canonical example of optimization problem is design. You want to find the system that optimizes some performance metric, maybe subject to constraints. So if you're designing a car, you want to minimize the drag subject to some operating type constraints. You may want to design energetically optimal flapping motions because you're looking to design MAVs. If you're the Department of Defense and you want to do some sort of low-cost reconnaissance and surveillance type vehicles. You can also think about applications in control. You want to drive a system towards some desired state. You might have flow coming over some sort of pipe here. You'd like to delay the onset of turbulence, so you can use add some controllers onto the boundary. You inject and suck fluid out at specific locations, and you can delay the onset of turbulence potentially. You can also look at more sophisticated applications with cloaking. You can also pose inverse problems as optimization problems. So just a bunch of examples here that I wanted to show that optimization problems really do come up everywhere. And this is one of the applications that I try to solve in my research. So inverse problems, if you're not familiar, there was a talk a couple weeks ago by a professor out of UC Austin. What we're trying to do in this context is we want to infer some problem setup given some downstream measurements. So let's think about one application in source inversion. I know that a contaminant has spilled somewhere. I'm able to measure some of the concentration of the contaminant downstream somewhere, and I would like to figure out where it originated. So this is me not knowing the initial condition of my problem, basically, and I'd like to figure that out. You can pose this as an optimization problem. So hopefully it just convinced you that optimization problems are quite important. They do show up in a lot of different physics applications. Let's pose it mathematically and introduce some methods so we can try to solve these. I'm not even sure which way to look here. Let's look up here. Okay, so if let's pose the problem abstractly. We want to minimize some objective function. If we're designing a car, this is probably a subjective function called the drag. It's going to depend on two variables. It's going to depend on the state of your PDE, which I'm calling U. This would be like your pressure and velocity and things like that. The variables of your Stokes equation are in your design domain. And then you're going to have some design variables, which I call mu. So this would, for example, control the shape of your car. You might have some constraints, and then you're going to have, of course, your PD. This is PD constraint optimization after all. So this is the problem that we want to solve. So if you're not familiar with how an PD constraint optimization solver works, I want to give you a very high-level overview so we can kind of all be on the same page. We're going to have three main components. The first one is our optimizer. We need to have some sort of a program that's going to be able to do mathematical optimization, minimize f of x subject to some constraints. It knows nothing about a PDE. It's just solving an optimization problem, converging until you hit optimality condition, or iterating until you hit optimality conditions. You're going to have your primal PD, this is your PDE solver, and then you need something called an adjoint PDE, which I'm going to talk about shortly. So the way this works is your optimizer is going to send your parameter configuration, the shape of your car, for example, to your PDE, and you're going to solve it. You're going to return the value of your objective function. You're going to pass all of your information to your adjoint PDE. You're going to solve the adjoint PDE. That's going to return your gradient. And now your optimizer knows the objective function and the gradient for its particular parameter, and it has all the information it needs to update its step. And you can iterate until you converge to something that satisfies optimality conditions. Okay, so I can't actually solve these optimization problems yet because I'm currently working with PDEs. I can't really do optimization over function spaces in a computer, so we have to discretize. So I just want to mention one slide on how we do this discretization. We use pretty new high-order methods that are to try to do this, these discretizations efficiently. As I showed on this slide right here, we're going to potentially have to solve these PDEs many times. So having efficient ways to actually solve them is really important if you're doing optimization. So first thing we're going to do is we want to be very general. So I want to possibly be handling moving and deforming domains. This is, think back to that flapping wing problem. Your entire domain is moving, deforming, it's parameterized. It can be a real mess to handle. So instead of working on our physical domain, we map to a reference domain. People that are in my finite element class, this is very similar to this isoparametric concept that we've been talking about recently. Next thing we have to do is we have to discretize. We get a conservation law that's now defined on our reference domain, and now we have to discretize that. So we're going to introduce the semi-discretization approach, where we're going to discretize in space using a discontinuous Lurkin method. Not going to go into the details of that. That's not part of the talk. But there's obviously a lot that goes in here. There's applying some sort of standard discretization technique. You get a whole system of ODEs. Now we need to integrate those ODEs in time. You have to use some sort of a numerical integration scheme. And this is what I'm going to use here is going to be called diagonally implicit Runge-Kutta schemes. So if no one's ever heard of these are pretty cool. These are, so if you've heard of implicit Runge-Kutta schemes, they usually couple all stages together. So you have to solve, would be your butcher tableau, it's usually dense. You have to solve for all S stages simultaneously, which leads you to very large systems of equations that can be very difficult if your PDE discretization has 10 million unknowns. And now you all of a sudden have S stages. So what diagonal implicit Runge-Kutta is, they have a butcher tableau that's diagonal. So you can solve one state at a time, one stage at a time. And then to get to stage 2, you just substitute stage 1 into stage 2, and then you can solve for stage 2. Substitute stage 2 into stage 3, and then you can solve for stage 3. So they're implicit, they enjoy a lot of the nice properties, stability properties of implicit methods, but you don't have to solve this combined system, and you can be higher order. And then we have to discretize our quantities of interest, like our objective function or our gradient. Okay, so once we have this, I'm just going to write my objective function or my any kind of output that could be a constraint or an objective as f of mu here. And now if we're going to do an optimization, like I said before, we need its gradient. We need to be able to compute gradients to be able to have any hope to do optimization where the function evaluations are very expensive and potentially have many parameters. So if you use the kind of standard chain rule of calculus, you're going to get this expression for the gradient of f. You have the partial derivative with respect to mu, and you have the fact that the states depend on the parameter also, so then you get these chain rule type products out here. And if you just look at this, this is a big red flag. These terms in red here, first of all, they're huge. Right? The number of rows here is the number of dimensions in your PD discretization. So think of that as 10 million. Now the number of columns is the number of parameters. You can easily have 100 shape parameters. So that's a 10 million by 100 vector and it's dense, or matrix and it's dense. So that's very expensive to store. It's also very expensive to compute because each column of that, you need to do an entire linearized CFD solve. So it's very expensive to actually to compute and store. So you're in trouble if this is what you have to rely on. But luckily we have this thing called an adjoint method, which essentially allows us to compute this df term without needing these sensitivities. Without going through the derivations, I just want to show you the adjoint equations and then show you what we can actually do with them once that we have them. So here's our adjoint equations that correspond to the discretization on a couple slides ago. Something to note, they're linear. These are linear equations. We're computing, it comes from a linearization process. They're always linear. They're solved backwards in time. I tell you the adjoint variable at time n, and I tell you how to go from time n to n minus 1. They depend on your primal state, so you first have to solve for your primal PD state, and then you can actually do the adjoint equations. They're also going to be depending on a chosen output. So if I have one objective function and 3 constraints, you have to solve 4 adjoints if you want to get these derivatives. So that's kind of the mechanics of the adjoint method, maybe not so interesting, but what is cool is this equation right here. Now I can actually compute this derivative that I cared about. All I need to be able to do is get the partial derivative of f, which is easy, and then I need to use these adjoint variables, and I can reconstruct that gradient, and all those du, d mu terms are gone, which is what's really cool about the adjoint method. So this is kind of some of the work that we've done in this direction. Now let's just see what we can actually do with it. So the first thing we're going to do is go back to that energetically optimal flapping flow. If you don't know anything, you're probably just going to start flapping randomly, and you're going to produce a lot of energy, and you're not going to have any kind of control on your thrust. But if you want to actually run this through a PD constraint optimization loop, you can actually get out a flow that requires half the energy, and you can exactly satisfy thrust constraints. If you want to allow yourself to actually do some local deformations, it's a little bit hard to see, but if you look at the top, it bends to conform to the flow. You can actually get even further improvements. So that's nice, but where you can really start to see improvement is when you actually allow yourself to vary speed. The adjoint methods have to be modified now because your time domain is in some sense parameterized, because you're parameterizing frequency, which is parameterizing your period. So this complicates the adjoint equations a bit, but what we were able to actually work with some more experimental people on this, and we had some nice conclusions that we drew. Okay, obviously initial conditions horrible. If you don't need much thrust, what the optimizer was telling us is it doesn't really necessarily matter how you pitch or how much amplitude you have, just slow down. Don't flap very fast. And that's what can get you very, very little energy required to do that. Now, obviously, if you need more thrust, then you have to start amping. But that's, like I said, those are some conclusions that we were able to draw. You can do the same thing in 3D because of this adjoint method is pretty efficient. You can easily code this up and do it in 3D, and then you can get to similar conclusions. So another application of this approach that I want to mention real quick before I move on is this is what goes into this inverse problem. So I'm working with a medical team in Sweden that wants to get very high resolution MRI images. Well, I guess MRI images are redundant, magnetic resonance images, and they want to have very low scan times. So anyone who's familiar with MRI, there's this fundamental trade-off between how long you leave your patient in a scanner and the resolution that you're going to get out of it. There's also kind of this thing that makes things additionally tricky is that if the more resolution you want, the more noise that's going to be here. So there's this kind of fundamental trade-off between scan time, resolution, and noise. And what we're trying to do with these optimization adjoint methods is break that barrier. So this is actually MRI data that they gave us. It's not in a person, it's just a little water tank here that they attached a hose to and did some sort of pulse. And this is what you get. You get flow data, you get velocities as a function of space and time, but you only get them averaged. You can't really see it here, but there's a bunch of little squares here, and you just get essentially a constant velocity inside each voxel. And what we'd like to do is we'd like to take this data, somehow couple it with our CFD simulations, figure out what should all the free parameters of CFD simulations be, namely boundary conditions, initial properties, material properties, things like initial boundary conditions, initial conditions, and material properties. And then once we have that our CFD simulation is somehow certified with MRI data, and we can trust it to actually use it to make medical decisions. So just to test kind of how a framework like this works, here's our MRI data. You can see it's synthetic at this point. We have, it has some noise added to it. Well, after we do this whole optimization procedure, this is what's in our code, the corresponding quantity from our CFD code. That we essentially minimize the discrepancy between these things, and this is what we get. And then your reconstructed flow looks like this. So the idea now is that instead of having productors to work with this kind of thing, we're giving them this to work with, and we know that it's somehow certified with the actual data that they took, measurements that they took. You can add some noise to this, and we can actually reconstruct very similar, very similar flow. Now we actually did this with the actual data they gave. We way downsampled the data that they gave us, and what we were actually able to show, which was a pretty cool thing for this method, this is the flow that we can reconstruct. So I guess your options, if you're a doctor, is to use this or to use this, which I mean it's maybe obvious which one you would want. And what we showed with this is that if we were to actually compare the measurements, the velocity measurements, to PIV data, which is considered to be much more accurate than MRI, we get closer using our CFD data than you would by using low resolution or high resolution MRI data. So there's something kind of fundamentally good or correct about what we're doing in this method. And like I said, it really just comes down to solving an optimization problem to fit our CFD simulation to the data that we're given. Okay, so one last extension that I want to mention to this before I move on is what happens now if we have multiple physics? Instead of just a fluid simulation, what if we have fluids and we have structures, or we have particle-laden flow, or if we have magnetohydrodynamics, or we have multiple types of physics interacting? We want to be able to do similar things with the adjoints. We want to have similar solvers, things like that. So if we want to take what people would call a monolithic approach, which is ignore the fact that everything comes from different physics, think of this as one monolithic global system that we then discretize using all of the standard techniques that I've already introduced, then nothing really changes. But this isn't always practical. A lot of people are going to have a structures code, and they're going to have a fluid code, and now they're going to want to have a fluid structure interaction code. So it's a lot of work to actually go in there and do a monolithic formulation. But what we'd like to do is be able to use those individual pieces and generate a partition that's called a partition solver, so we can still solve using these two separate codes. And we would like to have a high-order stable method. And what we did here is we repurposed implicit-explicit schemes. So let me rewrite implicit-explicit IMAX schemes, run schemes. So what we did is I rewrote these equations. These two equations are exactly the same, my pointer's dying, as the two equations below. But in the second equation, I added and subtracted a term. This term is RU1 comma C1 tilde. Right? So they're exactly the same. You can add and subtract a term always without adding any error. And now what I'm going to do is I'm going to choose the blue to be handled implicitly and the red to be handled explicitly. And the C tilde is a predictor. So these C terms here, these are coupling terms. This essentially says, how does my first equation couple to my second equation? How does my second equation couple to my first equation? These are coupling terms. So what we're doing really is we're predicting the coupling term, and then our explicit step is going to correct it. And what's really cool is that if you look at the stuff in blue, I can solve the blue system, the second blue system. It only depends on U1. I can solve it without having to even look at the U0 system. Once I have that solution, I plug in to this first system, and then I can solve that guy for U0. So you can essentially do the implicit solves without having to communicate a lot of stuff between codes, and then you do this explicit correction step. And since this inherits exactly all the stability properties from IMAX schemes, we get exactly the high order and the stability that you would get from IMAX schemes. And then you can do the whole adjoint derivation that I skipped, but you can do it. It becomes quite messy. But then what the adjoints inherit actually is an explicit-implicit structure. Remember, adjoint equations go backwards in time. So if forward you're going implicit-explicit, in adjoint mode you're going explicit-implicit, which is just kind of I guess, not important, just interesting. So let's solve some problems. So now you can look at particle-laden flow. You have light particles here on the left. They kind of swirl around and advect with your flow. On the right, they're heavier particles, so some of them get lost as you go through, and then some very kind of canonical fluid structure interaction problem that you can actually do with these solvers without ever having to throw away your existing codes and rewrite one that handles monolithically fluids and structures. Okay. Now we can also look at an optimization problem, very simple one in this context, where we're looking to do energy harvesting. So I have an airfoil that's going to be placed in some sort of a flow. It's going to be attached to a damper that's going to be storing my energy. And what I'm going to do is I'm going to start inputting energy to the system to pitch the airfoil, and then it's going to catch part of the flow, and then it's going to start causing to store energy in the damper. And we're trying to figure out exactly what alpha or angle I should pitch at to store as much energy as possible. I want to maximize the energy stored minus the energy input. And just a little movie here as what kind of the optimal solution would be. But it's kind of what you would expect. You want to pitch essentially as much as you can so you can kind of get most of the body facing the flow, so it has the most vector in the vertical direction, force vector in the vertical direction. Okay, so that is really what I wanted to say about these adjoint methods and how we can use them to solve a bunch of interesting problems across a number of different engineering and science applications. One thing I didn't talk about at all, which is very, very important, is computational cost. We have to, like I said before, when we do this sort of an approach to optimization, you send all of your information to your primal PD, you solve it. You send all your information to your dual PD, you solve it. That's one iteration. Now you keep iterating until you converge. Sometimes it's 10, sometimes it's 25 iterations, and every time you have to solve these PDs again. It can be very expensive. So one thing that we want to do is figure out ways to make this cheap. So the way that I've approached this is I'm going to introduce inexactness. I want to be able to solve the PDs inexactly, and hopefully inexactly and very efficiently. And then I want to use those inexact solves to get me to the solution that I'm looking for. So let me pose this abstractly. I have some expensive optimization problem, minimize f, and I want to replace it with something cheap, minimize m, or m is some cheap approximation model. Okay? I can always do this, but of course I need to have very specific requirements on m if I want this to be all useful. So that's what we have to think about now. Now, the way that we're going to actually ensure that this is useful is we're going to manage the inexactness. We introduce inexactness for speed, and then we have to manage it to make sure it still essentially gets us to where we're trying to go, namely to the solution of minimize f. So here's how we manage it. We use these things called trust region methods. So we're going to embed this in a globally convergent trust region method, which means we're not going to just minimize m. We're going to minimize some local model subject to some trust region constraint. We're going to say, well, I know that m is only an approximation, so I'm not going to let it go wild. I'm only going to minimize it inside some trust region, and then I'm going to update my model, and I'm going to continue the optimization. We need error indicators to account for all sources of inexactness. And then we need to be able to, once our error indicators drop below some certain bound, we need to be able to refine it. I just realized that my mic's not on. Should I turn on now or not care? Okay. Okay, so here's the ingredients that we need to be able to do this. Obviously, we need an approximation model MK. Okay, that's fine. Now, we also have to be able to have an error bound on how far the approximation model is from the truth. And not just on its value, but on its gradient. We need to say the error between the true gradient and my approximate gradient is bounded by some function I'm calling phi here. And what's really cool about this framework is that it doesn't have to be a tight bound. This has to be an asymptotic bound. Because look, I have an arbitrary constant, zeta, multiplying it. So all I really have to know is that some constant exists where this bound holds. And then the constant has to be independent of iteration number, and it has to be a constant. It has to be independent of iteration. But other than that, all I have to know that it exists. So even if I can't compute it, for example, let's say you do some bound that involves Lipschitz constants. I don't care. Stick it inside that arbitrary constant out front, and this whole framework will still work. Okay, once we have this approximation model, we have to be able to refine our model until our error indicator, well, it's just completely dead, drops below some bound. If you have those three things, you're going to have global convergence. And when I say global convergence, I mean we're going to converge to the solution of the original problem. Not the model problem, the original problem. That's what's critical here. I don't care about the solution of minimize m. I'm only using that to get me to the minimum of f. Right? So that's what's really important here. So here's the algorithm that uses all these ingredients. So the first thing I have to do is I have to choose my model such that the error indicator drops below that bound given by the trust region convergence theory. After that, I'm going to solve my optimization problem inside my trust region. Only inside that radius. It's going to be minimizing m subject to that trust region radius. Once I do that, I have to assess how good did I do. So I'm really going to be looking at the ratio of how much my truth reduced compared to how much my model reduced. And then if that's very close to 1, meaning my model did a very good job, I'm going to accept the step. I'll probably make the trust region radius bigger, and I'll move on. If it didn't, then I'll reject the step and probably shrink my trust region radius. So I talked about how I'm going to introduce these approximation models, but I didn't tell you actually how I'm going to do that. So let me say what is involved inside this model here. To do that, I have to introduce to you this concept of reduced order modeling. I'm going to give you just 2 or 3 slides on it, more to gain intuition than to actually be able to do anything too useful, because this is just pretty standard. So what I'm going to do is I'm going to approximate my solution U. Remember, this is the solution of my PDE, so it's a very large vector. I'm going to assume that it lives in some low-dimensional subspace. So I'm going to write it as a skinny matrix times a small vector. And then the idea is that I freeze that skinny matrix, and then my unknowns are only in that small vector count. Then I plug that in to my residual, or my PDE equation, and then I do some sort of a projection, multiplied by phi transpose if phi is orthogonal, and now I have my reduced order model. It has few equations, it has few unknowns. And then the goal here really is to do a massive reduction. This isn't just a factor of 2, right? The idea is that we go from something that's, I don't know, order 1 million or order 10 million down to something that's order 10 or 100. We're talking about massive reduction. So this basis is ridiculously skinny here. I don't want to go into any more detail. I want to give intuition for what we just did. So if you think about what the finite element method does, a finite element method, you pose your PDE in some sort of an infinite dimensional Hilbert space, and then when you do the finite element method, you search for solutions in some sort of a finite dimensional trial space. That's what you essentially do when you introduce your finite element shape functions or basis functions. When we do reduced order models, we take this one step further. I say, okay, sure, now I have a finite dimensional space. I can actually search for solutions on a computer in it, but it's expensive. It leads me to large models. So what I'm going to do is I'm going to introduce a subspace of that finite element model, and I'm going to only search for solutions there. And the hope is that if I construct that subspace intelligently, then I should be able to get away with a much, much smaller one than otherwise. Okay, one more slide for intuition. This is like saying, let's say we want to solve this problem up here. We just have a nice oscillating airfoil, right? I could use the standard approach in computational physics, which would be to do some sort of finite element or finite volume approximation of this. So you mesh this region with triangles or quadrilateral elements. You make a local approximation on each one, and then you patch all those together, and then that's your solution basis. But that leads you to a large number of degrees of freedom. The other option that you have is, let's say I use these 3 modes. They have nice properties. They're global, and they're data-driven modes, so I can potentially get away with far, far fewer of these than if I were to use local polynomials. This is just kind of some of the intuition behind using reduced order models, at least in the way that I'm talking about it here. Okay, so now that we have reduced order models, we can construct all of these things that we need for the trust region convergence theorem. My model is just going to be my reduced order model. So it's going to be the solution of my ROM, and then plug that into my objective function. My error indicator is going to use residuals. It's going to be the residual of my primal, my PDE, primal PDE, plus the adjoint residual. Remember, these are error bounds on gradients. So I can't just have the primal residual there. I need to know how much error I'm incorporating into the gradient also. So that's where the adjoint residual comes in. And then we have to have this last step, which is adaptivity, which I mean to make sure I can refine my basis until my error indicator drops below whatever bound was given. So to do that, I'm going to use my solution, the solution of my high-dimensional problem at my trust region center, as well as the adjoint at my trust region center. And then the interpolation property of minimum residual reduced order models actually tells me that this phi at mu k is 0. So I don't even have to check that value on the right hand, which was the norm of the gradient of the model. It's guaranteed to essentially satisfy it if I have those 2 points in my basis. Now, obviously, I've been doing iterations throughout my trust region method, so I have previous information built up. So I want to use that to improve my prediction power. So I'm just going to store all of that, and I'm going to compress all of it, and then I'm going to also throw that into my basis. So this basis is generated from snapshots of my primal and adjoint solutions, and then it compresses all of the previous information. So we still have it, but it's not necessarily needed for convergence. You do all this, and you get this nice convergence property. All right, so one schematic, and then I'll show you how this kind of approach works. So the idea, let's just focus on that picture up in the top right. So what we do is we start at we have our initial condition, which is that circle. Up in the top is our optimal solution that we're looking for. We're going to sample our high-dimensional model there, build a trust region, and we're going to now optimize using only this reduced order model. This is going to get me to a new point in parameter space. I'm going to assess how well that step did, and then gather more information, rebuild my model. And then I'm going to just continue in this fashion. I think I had too much fun creating this image because I had a lot of steps there. And then this is the picture that you should keep in your mind, is that everywhere where you see a big red dot is where I sampled the high-dimensional model, the expensive PDE high-dimensional model, and then that blue line is essentially tracing out everywhere that my ROM took me while I was solving in the trust regions. So So this is using these inexact reduced order models inside these trust regions to get me toward where I want to go. But I'm always kind of monitoring them so they can't just kind of run free. All right, so let's see how this works on a problem of an airfoil design. So I have a NACA 0012. I want to morph this into an RAE 2822 by minimizing the difference between the pressure discrepancies. Okay? Whatever the optimization problem isn't too important, but we can do this. So you can see the blue is the initial configuration. Down here is the airfoil. Up there is the pressure curve. And then whether I used a traditional high-dimensional model-based approach where we don't use ROMs at all, we always solve the PDE, or if I use this proposed approach, we get to the right solution. We converge to our target solution in both cases. So then the question becomes, all right, great, you were able to reproduce what we could already do. What's the point? Well, the point is we can do it faster. So if I were to use just kind of a standard optimization approach, that's the black you see here. It takes, I don't know, 25 or 26 iterations to converge. But if we use this reduced order model method, 5 or 6 iterations we converge. So factor of 4 you get by doing this framework in this case. Now obviously we pay a price. We have to solve a reduced order model a bunch of times. But like I said, these reduced order models are way smaller, so this is almost no cost to actually do this. No additional cost to do the ROMs. So how does this work on a bigger problem? So now we're going to look at shape design of this airfoil here. We're trying to maximize the lift to drag ratio. This is actually a pretty large dimensional problem. It has about 70 million degrees of freedom. We have 4 shape parameters. We have the length of the wing. We have some localized sweep. So you can see there, that one's kind of swept back more than this one. You have twist, and then you have some of this localized dihedral. So this is kind of, you know, the wing is, it controls how much it pitches up kind of at its tip, toward its tip. So if we look at the optimized shape, it's amplified so you can actually see it. It reduces the drag count by about 2.2, it reduces the drag by about 2.2 counts, which is not a huge reduction, but it's non-trivial. And then here's the baseline shape, and there's the optimized shape. And we can see the shock on the wing becomes weaker, which is kind of what you want to do when you're trying to minimize drag. And what we did is we saved about our computation time is about 60% of what it was before. So our speed-ups aren't huge in this case, but actually I saw this as a pretty big win for this approach because this problem has a really strong shock in the wing. This is a Mach 0.85 flow. Reduced order models use global basis functions. A shock is a local feature that's starting to move around, especially when I start to change the twist. Reduced order models are inherently horrible at doing this. I have some research efforts going right now that are trying to overcome this limitation. So I'm using essentially reduced order models in a regime where they really should not be used, but the trust region framework doesn't care. It has to resample the high dimensional model quite a few times, but it still gets to the solution that we want. So by doing this approach, you're not really in danger of not converging. You might be in danger of not really speeding yourself up that much if your reduced order model doesn't have good prediction capabilities, but you're not really in danger of not converging, which is nice. This is a kind of a mark of robustness. Okay, this point works. Okay, so let's see. All right. I also want to mention one more thing. What happens if my PDE now has some uncertainties in it? So maybe you don't know some boundary condition on your PDEs, or you don't know it with certainty at least, and you want to be able to take into account the effect that uncertainty has on your optimization process. It's called PDE constraint optimization under certainty. It's a big field. People want to do this. But if what I told you before about solving optimization problems, if I told you that was expensive, this becomes completely unreasonable. Because now what we want to do is we want, for example, to minimize, let's say, the expectation of the drag, where that expectation is integrated over your stochastic space. So if it's an uncertain, like you might have a gust load that has some uncertainties in it, for example, you want to integrate over that parameter space. And each integration point that you're going to be evaluating at is a PDE solve. So now if we look at this PDE constraint optimization picture, now every time we pass our parameter to our primary PDE, we have to solve an entire ensemble of PDEs to be able to compute this expectation here. And then same thing, we have to solve an entire ensemble of adjoint PDEs to do this. So like I said, if PDE constraint optimization hard, PDE constraint optimization under uncertainty is ridiculous. So we really need to be able to use some of these approximation methods to have any hope of doing these unrealistic problems. And I'm going to take a very, very similar approach as before. But now we're going to use reduced order models for inexact PDE evaluations, but I'm going to use what's called anisotropic sparse grids to do inexact integral evaluations. Expectations are just integrals. I'm going to lay down some sort of a quadrature rule, and this quadrature rule is going to be using sparse grids. If you're not familiar with what that is, I'm not going to go into details on it, but they're very sparse. essentially quadrature rules that allow you to be adaptive in each dimension based on where you need refinement. So to show you this pictorially, if this is the ensemble of PDEs that's required by kind of the basic method, the standard baseline method, if you use sparse grids, the hope is that now you have fewer high-dimensional models to solve. So that's kind of one level of inexactness. And then the next step is to, now let's replace, because there's fewer of them, but they're still expensive, let's replace them with ROMs. That's essentially what I've done in this work. So if we look at this is taking this PD constraint optimization under uncertainty problem and replacing the expectation with an expectation only on the sparse grids, the sparse grid nodes. And then the next step is introducing the reduced order models, and this is going to be our final approximation model. This is what that MK would be, is this model right here. So it has these kind of two sources of approximation. Any error indicators I would have to take into account not only the error introduced by the reduced order model, but also the truncation error introduced by the quadrature, and then you can do this. So I'm not going to go through the details. Let me just show you how this works. So go through the problem. So I'm trying to solve the stochastic Burger's equation here. I have uncertain viscosity as well as uncertainty in my boundary conditions, and I'm trying to drive my system, my U, toward some U bar, which I just take U bar to be 1 here, in expectation, and then I have some penalization on my control. So the control that you get is going to look some kind of weird thing like this, and then here's going to be the solution of Burger's equation. This is going to be, the black is the mean, and then you can plot plus minus 1 and 2 standard deviations here. And this is what's so cool about this kind of a formulation, is that if you don't just get solutions of your PDE, you get statistics. So yes, it's way, way more expensive, but you gain from it too. So if we look at the performance, you focus on this column here. This is just showing global convergence. The gradient of my objective function, the true objective function, goes down about 4 orders of magnitude and only about 5 trust region iterations. So that's quite nice. But another thing I want to draw your attention to is look here. This is F at the initial condition, and this is M at the initial condition. They don't even match in the first digit. M is not a good approximation of F. It's very, very cheap. It has a very, very sparse grid, and it has a very, very poor reduced order model. They're not even close to matching. But what happens is that this model was helpful in reducing your true objective function. So we don't need accuracy when we're far away from convergence. We only need to start refining these things and making everything more accurate near convergence. Once you're close to convergence, the model is very, very good. It matches the many digits. But initially, it doesn't even match the first digit, which is perfect. That's exactly what we want. Let's not over-refine when we're far away from convergence. So if we look at performance, here's the cost. Think of this as the number of HDM evaluations. If we use some sort of a baseline method, you're talking about 10,000 evaluations of your PDE to actually solve this problem. That only has 3 stochastic parameters. Now, if we use some sort of a state-of-the-art method that would use sparse grids but no reduced order models, you're looking at 1 to 2 orders of magnitude reduction. So that's already a huge win. Now, if we use this method, it depends on how fast your ROM is. If your ROM is very slow, this is this method with a ROM that has no speedup. The speedup factor of the ROM is 1. It's as slow as your high-dimensional model. Well, you can't do any better, obviously. But if your ROM is only 10 times faster, and like I told you, these reduced order models can be reduced way, way down, you already win by a factor of, 2 to 5. And if your ROM's 100 times faster, then you have a full order of magnitude reduction compared to the state-of-the-art. And then if your ROM's free, you're kind of hitting your lower bound at this point. So there's no real reason to put any more effort in making your ROM faster. So this is the kind of the key takeaway I would say here, is that by incorporating both of these levels of uncertainty, we can solve this problem much faster than possible, because when we're far away from convergence, we don't care about making the model accurate. It just has to be good enough to get us toward, in the right direction. You can do this in 2D too. This is a little bit more interesting problem, but I'm going to go over it a little bit quickly. So what we have here is we have some inflow. We're going to have flow coming over here. It's going to pour over this step, and then it's going to recirculate in this region. What I'm looking to do is I want to minimize the vorticity in this region. My parameter is the inflow here at this wall. And then I have uncertainties in my viscosity throughout the domain and in this inflow region here. So you can see what the optimal boundary control is. So this is the uncontrolled case. This is the mean flow and then plus and minus standard deviation. And this is the controlled case. You can see that all this recirculation here is gone if you have your boundary control look a little bit like this. You blow a little bit to the right on the top and a little bit to the left on the bottom. And then plus and minus 1 standard deviation. It's pretty robust to variations in these parameters. So this did a pretty good job in basically minimizing the expectation of the vorticity in this case in that region. And then here's the quick plot of convergence. As the number of major iterations increases, this is essentially the effective cost of the high dimensional or the reduced order model method. And this is the state of the art anisotropic sparse grid only method. And you're talking about 1 to 2 orders of magnitude difference between the two in terms of cost. All right, so let me just wrap up this portion of the talk, then I'm going to get into this kind of other dimension of optimization that I talked about in the beginning. So we developed this fully discrete adjoint method that is based on higher order methods for solving optimization problems. There's a number of extensions. I didn't talk about all of them, but I did talk about the extension to multiphysics, how we can introduce this new partitioned higher order stable multiphysics solver, and then the adjoints corresponding to it. We talked about acceleration of these optimization methods using this rigorous multi-fidelity framework that can use reduced order models. It can use partially converged solutions. I didn't even talk about that. And it can also use sparse grids if you're talking about stochastics. And then I talked about a number of different applications. So that's the first part of this talk. Now let me talk about kind of the other side of the coin that I wanted to mention. That was how we use these kind of methods to do optimization of physics. But now how can we use optimization to actually make better numerical methods? Let me give you one example of why designing numerical methods can be challenging in certain regimes. So let's say we're interested in problems that have strong gradients or discontinuities. These problems show up everywhere, especially in compressible flow. You want to talk about vehicle reentry, supersonic flows, things like this. You're going to get shock waves, things like contact lines, stuff like that are going to appear. These in physics manifest as very sharp gradients, things like densities and velocities and stuff. So we need, if we want to have any hope of actually doing simulations based on these methods, we need numerical methods that are going to be able to be robust to these kinds of features. Okay? So let's look at a very, very simple problem. Let me break those previous applications down into something very simple. We have a 1D domain. Okay? I'm going to break this 1D domain into 2 elements. It's really hard to see, but there's an element here. This is one element, and this is another element. And I'm going to lay down some sort of a basis inside these elements. I chose to use Lagrangian basis in each element. That's, I think, 4th order, maybe 5th order. All right? And now what I want to do is I have a shock, or some sort of discontinuity here. Now let's use this basis to approximate it. Everything went beautifully in this element. It was smooth and constant, and everything was nice. Now in this element, everything went bad. You get these overshoots and undershoots that are well-known Gibbs phenomena. I'm not claiming I found a new problem or anything. This is a well-known problem. Now let's say that this variable right here is your density of your flow. It just dropped below 0. So now your code crashed. And now if you're a grad student like I was when I was back at Stanford, now you have to go figure out how you need to tune these parameters so on the next run it won't crash. Then you have to wait for nodes, and that's really annoying, right? So this kind of thing happens a lot, especially if you're working with kind of legacy finite volume codes that use things like limiting. Okay, so that's one that's a big issue. How do we deal with this? How do people deal with this in general? Well, I just mentioned limiting. One thing that you can do is say, well, in this element, let me drop my order of approximation down to piecewise constant. Cool. No more overshoots and undershoots, except my approximation's horrible now. So what people do is say, well, just refine your mesh, and then everything works nicely. And that's true. So another thing that people would do is they would say, well, let's replace this discontinuity with something smooth. I don't like discontinuities. I can deal with things that are smooth. All right, good. Let's replace it with this guy. You fundamentally changed your problem, so that's maybe an issue, but you can still do this. Then you approximate. Well, it doesn't look so good because it's a pretty sharp gradient still. Well, good thing we can refine our mesh and everything works out nicely. So what are the issues here? The issue is that if you do that first option limiting, you have an order reduction. So you had a nice high order method, and now all of a sudden it's not. It's low order, especially around the shock. So that's an issue. And then no matter what you're doing, you're always talking about local refinement, which can be very tricky to do in 3 dimensions, especially if you have curved elements. It can be a real nightmare to do. So these are kind of the issues with these standard approaches. What I'm proposing is a very simple solution. All I want to do is I want to take features that exist in my basis and align them with features in my solution. So when I say features now, I'm talking about discontinuities, obviously. I can support discontinuities at the interface between elements. So if I can somehow magically move the interface of my element to exactly where the shock is sitting, I've essentially solved this problem. Because now I've perfectly captured the shock with this feature in my basis, and then on either side of the shock, the solution is smooth. It's constant in this case. So this problem is gone if I can do this. That's a big if. So this is what the next part of the talk is about, is how we can actually use optimization to do this. So here's the goal. We want to align element faces with an unknown. That's the key, is that I don't know where these discontinuities lie. That's what makes this problem hard. Otherwise, you could just mesh them. With the unknown discontinuities, so I can perfectly capture them and then approximate the solution on either side of it with using my nice high-order smooth basis. All right, so here's my non-aligned solution. Obviously, it looks like crap. If you do some alignment, especially if you do high-order alignment, everything looks really nice. Okay, so here's the ingredients of the method. This is going to maybe get a little technical, but this is what you need to make this approach work. I use discontinuous caloric and discretization because you need to have a jump between your elements. You need to be able to support jumps between your elements. So finite volumes could also be a candidate for this. What would not be a candidate for this is a standard finite element method, because that doesn't allow you to have jumps between elements. So you need something that is usually designed for hyperbolic problems, like finite volumes or discontinuous caloric. We're going to use optimization, and this optimization is going to do this tracking thing for us, and then we need a full space solver, and I'll get into this in a second. Okay, so here's the optimization problem that I'm going to pose. It looks a lot like the optimization problems from the previous part of the talk, but it's for a much different purpose. I'm not solving an optimization problem here. I'm trying to make a more stable numerical method. Right? So here's my optimization problem. Minimize f subject to, it depends on u, which is my PDE solution, and now x is the nodes of my mesh. So the idea is I want to move the nodes of my mesh around so I can minimize this objective function. And obviously I have my PDE constraint down here. This objective function has to have some properties. It must attain a minimum when the mesh aligns with the shock, obviously. I mean, I introduced the problem, this optimization problem, specifically to make this happen, so obviously the objective function has to have this property. The other thing that has to happen is that it must approach that minimum monotonically. If it has the right minimum, but it approaches it and it's super choppy, you'll get stuck. You'll get stuck in a local optimum trying to find it, and this won't work. So the other thing is that we have to observe is that we can't use this nested approach to PDE constraint optimization that I mentioned before. Right? Remember that nested approach relied on, give me a parameter, I'm going to solve my PDE, then we update the parameter, then I'm going to solve my PDE, et cetera, right? Now my parameter is the mesh. So if you give me a mesh that's not aligned, your simulation might crash. You might get a density that drops below 0 and you can't even solve it. So we have to find a different approach that doesn't rely on repeatedly solving the PDE. So these are some of the innovations that have to come out of this type of an approach. Okay, so now let's look at what I just decided to use as the objective function. So I'm calling f shock, my shock tracking objective function. It's going to be my finite element solution, and I'm going to subtract off its element-wise mean. It's very simple. It's the solution minus its mean integrated over that element, and then you sum over all elements. Very simple. We have to add on some regularization terms so the mesh doesn't invert. So I add on some term here that penalizes mesh distortion. These expressions are kind of nasty, so I'm not going to show them, but they're very standard. If you look at any kind of paper on high order mesh generation, that would be straight out of that paper. Okay, I want to show you properties of this objective function, so let me do a very simple example. Here's a 1D problem. We're going to look at this node, and then here's my solution. Now if we solve this with this DG method, obviously everything's going to be really nice and elements away from the shock, but in the shock it's going to go crazy. Now I'm going to start moving this node. I'm going to start sweeping it this way, and then I'm going to plot the objective function. So as I sweep it, you're going to eventually become perfect, and then it's going to get worse again. So I'm going to plot the objective function as a function of the position of that node. And here's what we get. So the first thing to notice is this is where the shock is. It has a minimum at the shock location, so that's check. And also it's monotonic. Within half of an element on either side, it monotonically approaches that minimum. So this is exactly what we wanted to see. You need this if you want to have this approach work. And it doesn't matter if we have polynomial degree 1, 2, 3, it doesn't matter. It's still essentially perfectly monotonic. And you can say, well, why not use something a little bit more sophisticated than just this weird U minus U average thing? Well, we can look at those. Accidentally turn this on, I guess. So if we look at something that's like a residual-based indicator, they actually do have the right minimum if you were to zoom in on that point, but obviously they don't satisfy the monotonicity property. They're super, super oscillatory as you approach. Another thing is you could use some sort of physics-based indicator, like the Rankine-Hunio conditions. And again, they have the right minimum, but super, super oscillatory. So these are reasons that I tried a bunch of different things when I was coming up with this objective function, and the simplest thing was the winner because of the monotonicity property. Okay, now let me say a little bit more about this whole nested approach that I was talking about before. we can't use it, right? I discussed this quite in detail before on how this nested approach works, because if I have to solve my PDE when X is not my perfectly aligned mesh, my simulation crashes. So we have to do something else. And this something else is called the full space approach. So what I'm going to do is I'm going to drive my solution and my mesh to their optimal values simultaneously. Now this is quite different from what I was doing before, right? Because before I would update my mesh or my parameters, and then I would solve my PDE. I would completely converge my PDE. Now I'm not doing that. I'm just basically updating these things simultaneously until everything converges to what it should be. All right, so how could you do this? Well, let's form the Lagrangian of our optimization problem. F minus lambda transpose R, and let's look at the KKT conditions, the stationary point of that Lagrangian. Optimization theory says that the solution of the optimization problem, minimize F subject to R, this is going to be essentially, this is the first order optimality condition of that problem. So you have essentially three equations here, three systems of equations. You have three variables, your U, your X, and your Lagrange multipliers lambda. Solve this huge system of equations. That's basically what this amounts to. So you can apply some sort of quasi-Newton method for this after you use some globalization strategy with either line searches or trust regions. And this is basically the solver that we have for solving this, for basically doing this, taking U and X to their optimal values simultaneously. So let's see how this works. So I already showed you this example, so maybe I already gave this away. But if you in this case where we're just trying to do a projection onto a mesh, if nothing's aligned, it works very poorly. If we only have linear elements, it doesn't look great, but it's obviously a lot better. And then if we allow ourselves to have high order elements, it looks beautiful on a pretty coarse mesh. So this is kind of the intuition for what we're trying to do right here. Now let's look at how this actually works with the PDE. That had no PDEs involved there. So here we have a Burger's equation. It's modified. We have a kind of a source term here, and then we're also going to have a discontinuous source term here. But we can derive an analytical solution for this. It's this 2 plus sign minus 2 minus sign thing that looks like this. Now if we apply this method, we get this red thing here is our approximate solution using this shock tracking method. And then these are the elements of your mesh. We have 5 elements here, and we approximate the solution with the shock basically perfectly. If you were to start doing mesh refinement, nothing really changes. So we're just kind of the same. Okay, so let's look at convergence. What's very hard to get is high order convergence when you have problems with shocks. It's really hard, and that's actually kind of what we did here. We showed, at least in the L1 norm, is that as we increase the number of elements, we get h to the p plus 1 optimal orders of convergence for this problem. So we go from first p1 all the way to p6, I think, and we essentially get the optimal convergence rates, which was, like I said, when you deal with problems with shocks, is really challenging to do. That's what this tracking method allows us to get. Now let's compare this method to, let's say, standard methods. So if I look here at this discontinuity tracking approach, it's these solid lines. It's the solid lines which kind of are the ones that lie on the bottom, meaning the lowest error for a given number of elements, which is exactly what we want. If we compare this to, let's say, the worst thing it could do, which would be uniform refinement. And every time you update the mesh, refine every single element uniformly, and that's known to be only going to converge at first order, and it essentially has, for a given number of elements, orders of magnitude more error, at least in this L1 norm. If you do some sort of an adaptive refinement, which try to find the shock that's got the element that's got the shock in it, and then refine, and then find the element that's now got the shock in it, and refine, something smart like that, you get this kind of curve here, this dotted guy, which asymptotically can approach the correct order or close to it, but I mean, you still have kind of an orders of magnitude difference between doing an actual tracking approach. Okay, last thing I want to say before I conclude is that we can do this in 2D, which is more interesting. So here's a circle, or a quarter circle. We have flow coming in this way. You're going to get a bow shock that's going to develop. And see how this works. So if we don't do anything, the solution looks horrible. This is a very, very coarse mesh. Obviously, we're not going to be able to solve this very accurately at all. Now, if we do tracking, P1, linear elements, doesn't look very good. Like I said, very coarse mesh. But even if we allow ourselves to have quadratic elements, it looks almost perfect. And the error in this case is 10 to the minus 4 or something on a mesh that only has 48 elements. Let's look at the mesh. The meshes are nice, that you can see that they're curved. Like this element right here, for example, curves to the shock, so that they can form in a high order way to exactly what where the shock is. And if you go third order, fourth, or P3, P4, whatever, it still kind of works the same. If I look at the actual shock tracking error indicator plot on each element, you can see that in the non-aligned case, it's lighting up all of the elements that are kind of violating or basically intersecting the shock. Then once we do the tracking, kind of everything reduces down. We minimize this quantity over the entire mesh. So we expect that once we start running the optimization process, where we get there. So now let's just look at a movie of how this thing converges. Quite a few iterations that it takes in this case, but that's not uncommon for optimization approaches. What's key here is that nowhere is this a valid solution until the mesh converges. We're always essentially iterating both the mesh and the solution and until they both converge together. And then voila, you have essentially the solution. And that's, like I said, this is critical for this approach to work. We couldn't do a nested approach because of simulation crashes. I already mentioned the error. So let me just, this is my last slide before my conclusion. So, and this is just trying to drive this point home one more time about this full space solver. Here's the residual, it's in red, and here's the objective, it's in black. This is the residual. It's never 0 until the final iteration, when the objective function has kind of hit its minimum. So that's kind of essentially the key to making this method work. Now, just to conclude, so what I did in this part of the talk is I talked about a way to use optimization to make better numerical methods, as opposed to the first part, which was actually using it for the purposes of discovering new or improved physics. The key innovation was this objective function and this full space solver. We got optimal rates of convergence, and there's still some work to do here. We have to look at things like numerical fluxes, we have to get better solvers, and then also topology changes in the mesh. I mean, it would be much better if we could actually allow ourselves to collapse elements or flip faces on elements than actually have to move everything to the shop. So there's still work to be done here. But with that, I'm going to stop. I've got us pretty much ended on time, and be happy to take any questions. Yes.
So for the second, so for this one, discontinuous mesh.
Yeah.
Shot. So what if the system is dynamic?
Yeah. So I haven't done any unsteady problems yet, but you could do this kind of an approach with a standard method of lines approach, where you just every time step you're solving an optimization problem instead of like a nonlinear system. So you could do that for sure. It would be inherently an implicit method. This wouldn't even make sense in an explicit context. So you could do that. You'd have to do all sorts of mesh operations once your shot gets too far and you have to start flipping moments. So that wouldn't be ideal. What I'm actually more optimistic about is you could take a space-time approach for this. You basically think of you discretize you think about your domain is both space and time. You mesh that. And then you would then do this, because now your shock is just a shock in space-time. The moving shock is just a discontinuity in space-time. And you don't have to do the whole domain at once. You could do slabs, and it would be a reasonable approach. And because we operate on meshes that are orders of magnitude coarser than kind of the counterparts that you would need if you're actually doing limiting or artificial viscosity or whatever, I don't really see it as a big issue. It's something I'm working on right now.
The second part, you mentioned you use, when you consider uncertainty in the second part,
yep.
You use sparse gradient.
Yes.
And you replace the high-pass simulation with ROM.
Yes.
So I assume when you build the parametric ROM, you need high-pass simulation. So what the portion of the sparse gradient you still need the high-pass simulation to build the ROM?
Yeah, so what we do is, I had to skip over the details on this, but what we do is we essentially, once we have our sparse grid, we have to train the ROM on the sparse grid. So we use what's known as a greedy approach, and we will essentially sample the high-dimensional model on the centrist point of the sparse grid, use that to build the reduced order model, and then we solve the reduced order model on all the other points of the sparse grid, and then we find where the error is largest. Where the error is largest, we go solve the high-dimensional model there again, and then we update our model, and we continue in this way until we drop below some error threshold. So actually, when I showed the performance plots, that included all of that training, right? The reduced order, that when I showed the performance plots with the reduced order model approach, this includes all that cost. So look at the case for tau is infinity. That means your reduced order model is free, right? It's still not a free method because you have to build that reduced order model, and that building the reduced order model requires high-dimensional model solves. So you're exactly right, but that's taken into account in these plots.
So this is still like a problem dependent, right? So
What's problem dependent?
This is still like a problem dependent. If the response surface and parameter space is kind of not so smooth,
Uh-huh.
so So you still need a lot of
Yeah, that's, I mean, these methods that use these multi-fidelity approaches, they're super problem. I mean, the convergence theory works and is not problem dependent, but their performance is. That's what I mentioned before with the aircraft problem, right? This was a fundamentally bad problem for reduced order models. The convergence, it still converged, it still worked. The issue is you don't have guarantees on speed up, right? And that's going to depend on how good your reduced order model is at predicting things. If it's really good, you probably only have to build the reduced order model one time, you can get all the way to the optimal solution. And that would be perfect. But I mean, the more complex the scenario is, the more you need to tailor the reduced order model for it. So if I had in this problem a reduced order model that was very good for dealing with shocks, then it would have, I would expect a lot bigger speed up than this.
Thank you.
Yeah, of course.
I don't see another question, so thank you very much.
Thank you.